All right, let's dive right in. If you've ever found yourself deep in a calculus problem, stuck in a loop that just won't end, you are in exactly the right place. Today, we're going to learn a fantastic shortcut for one of integration's trickiest challenges. And trust me, it's a game changer.
You know that feeling, right? You're chugging along with integration by parts, you solve the first bit, and what are you left with? Another integral, and then maybe another one after that. It's super frustrating, but believe me, there is a much, much better way.
I mean, take a look at a beast like this one. With the standard method, it feels like you're just getting tangled up. Every time you apply the formula, it's like you're pulled deeper into this messy knot. It takes forever, and it's so easy to make a tiny mistake.
So, here's what we're going to do. We'll start by looking at that annoying integration loop. Then I'll introduce our elegant solution, the tabular method. We'll walk through how to build the table, see it crush a tough problem, and finish with a pro tip that makes it practically foolproof. Let's get started.
Okay, first things first, let's really get to the heart of the problem we're trying to solve. Why exactly is the standard way so, well, painful for these kinds of integrals?
We all have this formula burned into our brains, right? Integration by parts. It's an absolute classic, but the key thing to notice is that it's recursive. You're swapping one integral for another one, and you're just hoping that the new one is simpler.
For instance, if you were trying to solve the integral of x squared times e to the negative 3x, you'd set up your u and your dv, you'd apply the formula, and
yep, look what happens. You're staring at another integral that needs the exact same treatment. This is that dreaded loop. It's so tedious, and honestly, every single step is just another chance for a plus or minus sign to go wrong.
But what if I told you we could do all of those repetitive steps at the same time, neatly organized in a simple chart? Well, let's meet the hero of our story, the tabular method.
And you don't have to take my word for it. The folks at Geeks for Geeks put it perfectly. The tabular method streamlines the whole process. It makes it way faster and, crucially, way less prone to silly mistakes. This isn't just a party trick. It's a real upgrade to your calculus toolkit.
And the advantages here are just so clear. It is way faster because you're doing all the derivatives and integrals at once. The organization in the table just cuts down on the chaos. And best of all, you don't have to keep plugging things back into the formula again and again. It's just easier.
So how does this amazing method actually work? Let's roll up our sleeves and get into the nitty-gritty of how to build this table.
The process is wonderfully simple. You start by picking your u and dv, same as always. Then you make 3 columns, one for the sign, one for differentiating u, and one for integrating dv. You just fill them out, multiply across diagonally, add up the results, and you're done. Seriously, that's it.
All right, theory's great, but seeing is believing. Let's go back to that intimidating problem from the beginning and watch how this method just breezes right through it. Get ready for that aha moment.
Okay, here it is, the integral of x cubed times sine of x. We start with our nice, clean table. We're going to choose x cubed as our u. That's the part we'll differentiate. And that leaves sine of x to be our dv, the part we'll integrate.
First up, let's fill in the columns. In that differentiate column, we'll just keep taking the derivative of x cubed until it disappears. So we get 3x squared, then 6x, then 6, and finally, 0. Perfect. At the same time, in the integrate column, we find the integral of sine of x over and over. Negative cosine of x, negative sine of x, and so on.
Now for the sign column. This part is about as easy as it gets. You just start with a plus sign, and you alternate all the way down. Plus, minus, plus, minus. Simple as that.
And now for the magic. We just multiply diagonally to get our answer. See the arrows? You take the sign from one row, the term from the differentiate column, and you multiply it by the term in the integrate column from the row right below it. We're basically doing 3 rounds of integration by parts all at once without any of the mess.
And there you have it. You just sum up those diagonal products. The first term is plus x cubed times negative cosine x. The second is minus 3x squared times negative sine x. And you just keep going. No loops, no getting lost, just a straight shot to the final answer. How cool is that?
That was pretty impressive, right? But there's one crucial choice we made at the very beginning. How do we make sure we always make the right choice? Well, that brings us to our final pro tip.
You know, the success of this whole method really hangs on one key decision: picking the right function for you, the one you're going to differentiate. You always want to pick the one that gets simpler, the one that will eventually go to 0. So, How do you know which one to pick?
Easy. You use the Liate rule of thumb. It's a handy acronym that gives you a pecking order for choosing u. Whichever type of function in your integral shows up first in the word Liate, that's your u. So you're looking for logarithmic functions first, then inverse trig, then algebraic, then trig, and finally exponential.
Here's a perfect example of why this matters. Let's say you have the integral of x times e to the x. Well, x is algebraic, and e to the x is exponential. In Liate, a comes way before e, so we choose u equals x. And that's a great choice, because it differentiates down to 1 and then 0. If we had picked e to the x, we'd just be differentiating forever.
So Liate is an amazing guide for sure, but the real key is just practice. The more problems you solve using this method, the faster you'll get at just spotting the right u without even thinking about it. It'll become second nature.
And to wrap things up, I'll leave you with a little brain teaser. This tabular method is actually even more powerful than we've seen. It can even crack integrals where the differentiate column never hits 0, like the famous integral of e to the x times cosine of x. So, my question for you is, how might this table help you solve a problem that seems to loop forever? Think about it. Thanks so much for joining this explainer.